Hi there. So this video is to explain section 6.3 in the AP curriculum, all about rewriting definite integrals into sigma or summation notation. So we talked about the definition of definite integrals in class and how it was a limit as n goes to infinity, k equals 1 to n, f of x sub k times delta x. And remember, these were the rectangles. They got thinner and thinner. We wanted more and more of them to fit in the area more exactly. And this yielded a definite integral, where the delta x became dx because it was becoming infinitesimally small. The x sub k, which were individual values of x, just sort of became this continuum of x's, so it's just an x. And then this infinite limit of a summation is what this integral sign means. Now, we talked about that in class, but there's a step farther that the AP curriculum wants you to go. So I'm going to draw a picture here to sort of explain where the AP curriculum is going from here. So draw a little graph. I'm going to call this A and this B, and we're trying to get the area underneath this thing, right? So typically what we would do is we would subdivide the interval, and we're just going to keep it small for now. And we would label each of those with an x value. Let's say A is my x sub 0, my starting value, then x sub 1, then x sub 2. So this time B will be my x sub 3. Now, we're going to use equal subintervals here for the purposes of understanding what's going to be happening. So you know that the width of each of these is a delta x, and that the height of each of the rectangles that I would have, let's just use LRAMs here. The height of this would be f of x sub 0, then f of x sub 1, and f of x sub 2. All right. So if I were writing this sigma out, it would be the sum of f of x sub 0 times delta x plus f of x sub 1 times delta x, f of x sub 2, and all this should look familiar. Area is approximately that. And then if I write that as a sigma, k starts at 0. This time it can start at 1. That's fine too. This time it would end at n minus 1. If I used a right-hand endpoint method, it would start at 1 and end at n. And then this would be f of x sub k times delta x. Now, the difference in what the AP curriculum did and what we did in the past is this. They want this delta x and this x sub k written in terms of the number of subintervals that we built and the starting value, which is x sub 0. So what I'm going to do here is going to quickly explain what this is going to look like. So delta x, since the width of each of those intervals is equal, we can get the width of each of those intervals by taking the width of the entire interval, which is b minus a, and divide it by the number of intervals we divided it into, which is n. So delta x is the width of the interval divided by the number of subintervals. And then if I look at each of these individual x values in here, x sub 0, we know that. X sub 1, sure, that's a different x value, but you could also arrive at that by starting with x sub 0 and adding a delta x. Basically here, adding delta x moves me to a new spot. And then go to x sub 2, I could take that value and add another delta x. And so forth. So you notice whatever subscript on the x value I'm on, that is a multiplier on the delta x. So this is going to lead us to this conclusion, that x sub k is equal to my starting value x naught plus k times delta x. Now, we can use the stuff that's here in the bottom now, this red and this green, to take this definite integral and rewrite it in summation notation to the level that the AP people want us to do. So what they want you to do essentially is to rewrite. Let's go ahead and do the thing we know already before we get into that. So we should already be able to write this in summation notation. limit n approaches infinity, sigma, starting at 1, ending at n, or you can start it at 0 and end at n minus 1, depending if you're using an LRM or RM. Square root of x sub k, remember going back to the summation notation, plus 1 times delta x. Now, this again, we already did. Now, what we're going to do now is use the stuff that's in red and yellow to finish the process. So delta x is b minus a over n. b and a are 7 and 3. So delta x is 7 minus 3 over n. Now, x sub k is x naught plus k delta x. And x naught is 3. It's the value I started at. Plus k times delta x. But delta x, remember, we just found in the red. It's 4 over n. So my x sub k is 3 plus k times 4 over n. So that means when I rewrite the square root part, it's going to look like this. Where I replace that x sub k with that stuff written in terms of k and n. And then the sigma notation stays the same. So we're going to do one more example of this on the next page. This will be the stopping point, and we will be good to go. So I'm going to write one more on the next page, just an example without so much explanation. Let's do 5 to 11, though, just for kicks. Let's do the sine of x plus 3. So I'll rewrite in summation notation that we already know how to do. Over to the side, I'm going to find my delta x. b minus a over n, so in this case it's 6 over n. And then I'm going to find my x sub k. My starting value was 5. It's k delta x, so it's k times delta x. So it's 5 plus 6k over n. And then I'll write my sigma notation. And there it is.